Welcome and hello. This is a video exercise in RIMS. And in this exercise, we are going to be dealing with a basic reservoir operations. So let's go ahead and get started. I've got the RIMS interface up on the screen. I'm also going to bring up a schematic of the network. What we have is inflow to a reservoir. Downstream of the reservoir is node 1, 2, and then 3 over here to a diversion to the town. The town has a demand and the reservoir has a set inflow. Those will both be state variables. In the next slide, I have the different variables I'm going to be using. So for the inflow, I underscore res1. For the reservoir storage, S underscore res1. And then C12, O2, and D23 representing the channel flows between nodes 1 and 2, the outlet from 2, and then nodes 2 and 3. D representing the demand, C representing a channel flow, and then O representing an outflow. But of course, these are all going to be of kind channel. So let's move that out of the way for now and return to our RIMS. Actually, let's open up our project directory. That's right here. Let's go ahead and create a project first in RIMS, and then we'll go from there. Okay, so move that out of the way. I'm going to go right click, new, project, then next. I'm going to give this project the name E4, basic reservoir operation. And then right here for the location of that directory, I'm going to bring the project directory back up the screen, copy the path, and then paste it. Make sure your path has no spaces, and that looks good. I'll go ahead and click finish. What that did is it adds this .project file to your project directory. Next, let's go ahead and create a launch file for this project. So with our project selected right here, I'm going to go right click, run as, and then run configuration. I'm going to select Russell/RIMS2 application. Move this over here and resize this a bit. Okay, and then click on the new configuration. For the configuration name, I'll call it E4 Basic Reservoir Operations. And then further down at the main Russell file, we need to specify this is going to be in the run directory. I'll call it main.wresl. The decision variable file will be in a DSS directory. We're going to be setting up these file folders and directories in just a moment. Type what I type if you wanted to follow along. dv.dss. State variables will be in dss/sv.dss, and then the initialization will also be in DSS directory init.dss. Okay, further down for part A on the decision variable, we'll name that project. Part F of state, we'll call that state variable, and then the initialization, part F, we'll call that init. The 1 month time step is good. We'll start on this default start date, which is the beginning of water year 22. And let's just go for that one single water year of 1922. So I'll set the end date to 1922, September 30. That looks good. Next tab over for configuration, go ahead and click that and then check the checkbox on to enforce Russell plus compiler. This is something I've been skipping over in most of my previous videos, but it's something I want to start doing now. That way we can use the Russell plus reference manual and believe what it says and not have any errors when we type in things like dvar and svar and so on. All right. The last tab over is common. So go ahead and click that. Click on shared file and then the browse button and then navigate to our project E4 basic reservoir operations. Okay. And then click apply. We can close that now. And if we go back to our project directory, we have our launch file right here ready to go. Next, what I want to do is show the file structure that I plan to create for this project. Here's the project directory. We already have these two files down here, the .project and the launch file. Next, what I want to do is set up this file folder structure where we've got DSS folder, run folder, inside run folder, we have a lookup folder and a system folder, and then all the other lines here represent files. I should probably also add a state variable right there. Okay. So let's go ahead and start building that file structure. All right, so first up is new and then DSS directory. Inside that directory, I'm going to add a file. I'll just go down to text document, call that dv.dss. This is going to be for our decision variables. And okay, and then I'm just going to, it's a little quicker to make a copy, date variables, and then the last one in this folder is init, right, like that. Okay, I'm going to go up a level. All right, off camera, I built the run directory here. We have a main Russell file. Inside our lookup directory, we have an all data table. And then inside the system directory, we have the different components of the model itself: channels, constraints, demands, inflows, objectives, and reservoirs. All right. Let's go ahead and start adding some data to these tables. In fact, let's start with populating the init.dss file over in the DSS directory. So this is going to set the initial storage for our reservoir. We've got DSS view loaded up on screen, so I'm going to go ahead and open up that init.dss file. Here's the project directory. Here's the DSS directory. Here's init.dss. Open. Okay. There's currently no paths. That's fine. I'm going to create a time series data set. So data, manual time series data. And then for the path name, I'm just going to paste in what I have prepared here and then hit tab. So the path name parts have parsed into the A, B, C, D, E, and F parts right there. For the start date, this is going to be 12 months prior to the beginning of the simulation. So 12 months, basically the water year of 1921, which will start on 31 October 1920. I think this is right. 2,400 hours. The units is going to be in TAF, which is 1,000 acre feet, and then the type is going to be period average, this first option here. So 1,000 acre feet, remember we're dealing with the storage now. Part C in reservoir 1, our only reservoir, that's part B. And then down here for the data, I'm just going to type in a value of 120. And then I'll do that for each of the 12 months leading up to the beginning of our simulation. That way, the callback can reference up to 12 different time periods. So that's good. I'm going to click Save. All right. And we have our path right here with our data. That looks good. Next, I'm going to go ahead and open up the different file folders that are associated with the model, such as channels, demands, inflows, and so on. So let's go to Run and then System, Channels. Okay. I've got the channels.russell file up on the screen here. In previous exercises and lessons, I used args_channels.russell. Right now, I'm just going to go with channels.russell, see how I like that. Maybe I'll switch it back, but for whatever reason, I'm just going to try to keep it simple with the naming. All right, I'm going to open up the other files as well. So those are listed across the top. Let's start with this first one, channels.russell. I'm just going to be pasting in the code and describing it as I go. So these are decision variables. Since we checked on that Russell Plus interpreter in the configuration, that allows us to use the dvar variable. These are 3 different decision variables, which represent the flow through C12, O2, and D23. Okay, so we'll be referencing that after the model runs to see what those values are. All right, next up is demands. So here is demands. It's a state variable. UD_1 represents the demand for the town. So the diversion is going to satisfy this demand. We're going to be selecting the values from the demand column from the all data table where month equals month. Okay, so let's save that. The reservoir inflows is the next file, or the inflows file. And what we have is another state variable. I just pasted in svar. I_res1 represents the inflow to the reservoir each month. We're going to be selecting the value from the inflow column from the same all data table where month equals month. So this all data table we're going to be creating in just a moment. Next up is the reservoirs table. And boom, let's see what we have here. What I've done is I've actually added comments to each of these lines because this exercise is focusing a little bit more on the reservoir than the other components. What we have is 2 state variables, svar and svar on lines 5 and 8, and then 3 decision variables. This particular reservoir has a total volume of 150,000 acre feet, and that's represented by level 2. This is a simple state variable, so I'm just defining 5 and 150. What I have here for the label is that the storage capacity in the inactive zone is 5,000 acre feet, and then the level of the inactive zone and the conservation zone is 150,000 acre feet. So the usable storage in the conservation zone would be the difference, which is 145,000 acre feet. To keep track of the individual storage within each zone, that's what these 2 decision variables are, s_res1_1 and s_res1_2, representing zones 1 and 2. And then the kind here for part C in the decision variable path is storage-zone. So it's the storage just in that zone. And then we need to keep track of our total storage, which is s_res1. That's going to be the sum of the storage in each of the zones. All right, the next file over is constraints. Here we have continuity constraint on line 2 in the reservoir. We have the inflow minus the release equals the change in storage. And I'm also including this TAF underscore CFS as a multiplier to convert 1,000 acre feet to CFS in a 1 month time step. And then line 3 here is the continuity at node 2. So the inflow equals the outflow. The next constraint down, also a hard constraint, is the diversions. So the maximum diversion flow cannot exceed the demand of the city. And then finally, lines 9, 10, and 11 are our constraints for the reservoir. Basically, the storage in the zone 1 cannot exceed the total storage. Same thing with zone 2. And then the total storage in the reservoir is the sum of the storage in zones 1 and 2. The last file here is the objectives. So this is where we identify what we're trying to maximize. I have my decision variables here and then the weights right here. The highest weight of 1,000 is assigned to the storage in the inactive zone that has to be full. And then after that, we want to satisfy the demand to the town. That's D23. And then finally, we want to fill up the reservoir, that conservation zone. So that's why the weights are what they are. I actually have two more files I need to open up and edit. So let's go ahead and open up the main Russell file. I need to go up a level to main Russell, paste in the code I have prepared. We have one cycle. The model is going to be called base. It goes first, and I'm just going to basically be including those same Russell files that we talked about. A little bit different order. It's going to be demands, inflows, channels, reservoirs, constraints, and then objectives. All right, save that. The last file we want to open up is the data table. We need to actually populate the inflow values and the demands. Open and then look up. All underscore data dot table is the file. And again, I'm just going to paste in the data I have prepared. So you're welcome to pause the video and stop and copy it over if you want. But the first couple of lines are just comments. After that, we have the name of the table. The row below that is the name of the fields or the columns where we have month ranging from 1 to 12. That's in the where clause of the queries. And then inflow and demand. The inflow ranges from 27.7 up to a max of about 46.8 on a 1 month time step. And then it looks like it goes down to 26.5. I just made these numbers up. And then the demand to the city here is 5 for the first 7 months and then 6 for the last 5 months of the year, of the water year, that is. Remember, this starts in October. So month 1 is October, month 4 is January, February, March, and so on. All right, let's go ahead and run the simulation and see if that works. So let's save all those files, go back to our RIMS. I'm going to expand the, actually, hold on, I need a refresh here so I should see, good. I'm seeing all my folders and files here. On the launch file, I'm going to go right click and then run as and then launch. Okay, that ran. Let's go check out the results. I'm going to open up the dv.dss file, which is right here. Okay, let's take a look at our reservoir first. So here's the total reservoir storage and then the storage in each zone 1 and 2. I'm going to open up the table view first. Now we have the initial 12 months right here, which is before the simulation begins. And then here is the year of water year 1922. This is what we're actually running for our simulation. It looks like we are maintaining a constant 5,000 acre feet for zone 1. That's good. That was our highest priority. And then after that, it looks like we're able to increase the storage in the conservation zone. This is zone 2. And of course, the sum of these two columns is this right here. Okay, so that looks good. Pretty much what we expect to see. Let's take a look at the flows through the channel, diversion, and outflow. So I've got those three fields, or those three paths highlighted, and then click on the table button right here. Okay, so it looks like we are satisfying our urban demand, the demand to the city of 5 and then later 6 CFS each month. And that is the only flow we have through this channel 1, 2. So the outflow is 0, meaning there's no flow out of the system. So right here, we have a value of 5 or 6 through C12 as well as the demand, but then O2 right here gets no flow. So before we modify the reservoir, let's go ahead and just add a downstream inflow requirement so that O2 is going to be a certain amount, maybe something like 10 CFS. All right, so let's go ahead and close this up for now, minimize, and then bring out our tables once again. Here is the all data table. I'm going to add a new column to the far right called outflow min. I'm just going to paste in what I have prepared. The only thing I changed here was outflow min, and then I added a constant 10 CFS. So let's go ahead and modify the other files to accommodate what we need to enforce that 10 CFS minimum downstream flow requirement. I'm going to go over to the demands.russell file. I'm going to add another state variable to represent that in-stream flow. Okay, give myself a new line here. I'm going to call it SVAR river demand O2 for lack of a better variable name. And it's just going to basically be reading in the data from that outflow min column from the same all data table. Next, I'm going to go over to the channels file, the channels.russell file, and then O2, this is going to represent the total outflow, but I only want to prioritize or increase the objective function value in the LP solver for the minimum in-stream flow. So if there's additional flow, there's not going to be additional objective function value increase. All right, so I'm just going to come down here and paste this in. What I've done is I've added two more decision variables on these lines 4 and 5. O2 min and O2 extra. So the sum of O2 min and O2 extra will equal O underscore 2. So I need to add that in the constraints file now. Now under the continuity section, I'm going to add a line here. So line 4, I just pasted in. Continuity O2, it basically says O2 equals the sum of O2 min and O2 extra. While I'm in this file, I do want to also set a max river demand. So under this section here for max diversions, I'm going to set a max river demand, max RDO2. And what that means is the maximum value for this O2 min is going to be set to the demand, which we know this number is a constant of 10 CFS. All right, and then on the objectives file, I'm going to add this line right here, O2 min. So basically, we are going to be encouraging the flow in that minimum flow. And the weight I'm going to assign it to is 120, which means the flow downstream out of the system is slightly more important than the weight here, the diversion flow to supply the demand for that town, which has a weight of 100. Okay, with all of those changes done, let's go ahead and save and see what happens. So I'm going to save all the files. I'm going to go back to RIMS, Eclipse, right click, and then run as, and then run. Okay, let's check out what we have here. I'm going to go into my dv.dss file, view, refresh the catalog. I now see a couple more values here, new decision variables that we added. That's good. Let's look at those three paths for O2, O2 extra, and O2 min. So if I open up the table, this looks good. What we have is the total O2 is the sum of the extra plus the min. That min of 10 CFS appears to be satisfied for all 12 months of the year. So that's cool. So now if I look at the O2, the flow diversion to the demand to the city, and then just downstream of the reservoir, these three we had in the diagram, and then we open that up in the table. That looks good. We have the 5 or 6 CFS demand to the town, the in-stream flow of 10 CFS, and then the total is 15 or 16. All right. And the reason why it's the bare minimum is because we've also prioritized the volume right here in the conservation zone, which is zone 2. Even though 1 is a very small number, it's still positive, which means the reservoir is trying to fill up. So let's go ahead and take a look at those reservoir volumes. Here they are in a table format. The total storage begins at 120, and it increases up to 134,000 acre feet by the end of the year. Zone 1 is 5,000 acre feet the entire year, and then Zone 2, the conservation zone, it starts at about 115, and then it increases to almost 130,000 at the end of that water year. Okay, let's go ahead and make one more modification, and what I want to do is set a target storage for the reservoir. And what I want to do is say we want the target storage to be 130,000 acre feet. And if it's not, we're going to penalize it so that it will want to release the water. This number will stay at 130. I expect this to be at 5, and then this will stay at 125,000 acre feet. I'm going to take a look at the storage, total storage, and how about the zone 2 storage, the conservation storage in a plot. So here it is. Don't worry about the first half. That's the water year 21. We don't care about that. And then green right here is the total storage. Red right here is the conservation zone storage. So if we set a goal to fill up the total storage, this green line here, to 130, then that should level off at 130. And then the conservation storage should level off at 125. If that happens, then our O2 extra will not be 0 anymore. We're actually going to have values here. Let me open up all three of these at the same time. So this is going to be a non-zero number once that happens. Okay, so let's go ahead and make those changes to our code into the model and then run it and see what happens. The first thing I'm going to do is add another column to our all data table right here. So after outflow min, I'm going to add a res1 storage target. So let's see, let me make this a little bit wider. Yeah, so this res1 storage target, it's 130 for every month of the year. I'll be the first to admit I don't really like how I can't line up the numbers with the actual column headings. So I may modify my approach and actually put one set of values in their own table data in the future. But for now, I'm just going to go with this. But just so you know, we're going to have another state variable and it's going to be 130. So let's go ahead and build that. I'm going to put it in the reservoirs.russell file. I'm going to put it right below the S reservoir 1. So paste. Oops. Okay. So there it is. I should probably also give it a label. We'll call it reservoir 1 target. What it's doing is it's reading that value 130 for each month from that all data table. So instead of a simple state variable, this is a lookup state variable. And then the last thing I need to do is update the constraints right here and set a new constraint. This is a soft constraint now because there's a penalty involved. I'm defining the left-hand side as the storage in the reservoir, the right-hand side as the reservoir target storage. And down below here, I have if left-hand side is greater than right-hand side, there's going to be a penalty of 5. And then same thing if the right-hand side is greater than the left-hand side. So basically, there's a penalty if the storage of the reservoir is off the target either in either direction, too far below or too far above. Let's go ahead and save all these files and then go back to our RIMS, right click, run as, and then run. Okay. And then to our DSS view, our db.dss file, I'm going to go view, refresh. Let's take a look at our reservoir storage now. So now I'll open up the table. And here we have a constant 130,000 acre feet, which occurs in May and just continues on the rest of the year. 5,000 acre feet in zone 1, and then a constant 125,000 acre feet in zone 2, the conservation zone. So that looks good. And like I said, we should expect to see additional outflow starting this month here in May of 1922. Before we do, let's go ahead and just highlight these plots. The total storage in green, it levels off at 130, and then the conservation zone storage levels off at 125,000 acre feet, that is. All right, let's take a look at the O2, O2 extra, and O2 min, and then let's look at the numbers here. All right, cool. So the first half of the water year, approximately, this is what we saw before. There was no extra flow. The only flow was to satisfy that minimum in-stream flow requirement, which is satisfied for the entire water year. However, starting in May, we have extra flow right here because we don't want the volume in the reservoir to exceed that 130,000 acre feet for the total volume. O extra plus O min equals the O2 value in this column right here. If we want to take a look at that plot, here it is. In yellow here, this is the constant 10 CFS in-stream flow requirement. In red, this is the extra flow. And then, of course, the sum is in green, and this is the total flow flowing out of the system. All right, well, that is it for this exercise. What we did was set up a reservoir network system with a reservoir, a city with a demand, an in-stream flow requirement, ran the model, and then modified the rule at the reservoir to maintain a constant storage for the entire water year. Ran the simulation again and saw how the system responded.